Hey, what's up, guys? Chung here again. And so this time, let's take a look at another LeetCode problem here. Number 862. Shortest subarray with sum at least k. All right, so this is a hard problem here. So let's take a look. Basically, and you're given like an array, right? You're given like an array with integers, and you need to find out the contiguous subarray whose sum is at least k, right? And you need to find the shortest among all the possible subarrays is at least k. So for this one, we're gonna use a sliding window here. If you guys remember, there is like a similar problem where like if all the numbers, if all the integers are positive, and ask you to find the uh, the longest, right? Actually, the longest subarray whose sum is not greater than k, right? So for that one, we can simply use like a two-pointer solutions, basically with the left and the right pointer every time when we find the right positions, we will check if the current sum of the left and right is the same, is greater than k or not. So, okay, so another thing to get the subarray sum, we usually use a presum, right? Basically, we use this presum minus subtract the left pointer's presum to get the range sum. And for that one, if it which we basically we expand the right pointer to this current positions, then we will, if this range here is not meet does not meet the conditions, then we'll try to shrink the left one, right, until the sum between those two are within the range k, right? So and then we just keep traversing the string until we reach the end. And the meanwhile, we'll also be updating the an answer variable here. But what makes this problem a hard problem is that we might have like negative numbers, right, in between, so that we cannot assume every time when we move the left pointer closer to the right pointers, it's not guaranteeing that the sum in between will become smaller, right? Because if there's a negative one, if we remove the negative one, and then the final result will become bigger, right? Will become a greater than the previous sum. So then basically the similar question is here, right? Basically every time when we have like a new right pointer here, right? And how can we find how can we find the shortest, right? How can we find the shortest subarray whose sum is at least k? And a brute force way will be every time when we at the correct at the new right pointer positions here. Basically, we'll find all the previous subarrays, and then we'll use this presum to calculate each subarray's sum, and then we compare with this k, right? And then we just get maintain like a shortest length among all those subarrays, right? But that will obviously uh, exceeds the TLE because the range length is 5 to the 10. Yeah, it's 5 to the power of 5. Yeah, the range is like 50,000, and the to loop through all the arrays will have like n square and then another n to get the sum. Sorry, not the n. Basically, it's going to be an n square method here, right? To loop through all the previously subarrays, and then that'll be too much. That'll be too slow for this problem. If this one is a little bigger, then we'll certainly TLE. So, and then the problem comes to how can we efficiently speed up the process of finding the previously subarrays, right? Who could be who possibly could be our candidate. Mm. So and that's why this time we're gonna use like an increasing queue here, a monotonic queue to store all our candidates for uh for the previously uh subarrays, right? So why we can use a increasing queue to to help us solve this problem, right? So our goal is to so our goal is to find the shortest contiguous subarray with sum at each with sum at least k, right? Mm, so basically, we're gonna have like pre-sum. We're gonna calculate the pre-sum first for each of the elements here, and every time we're gonna be maintaining an increase queue. So the increase queue is like it's always it's strictly increasing. Okay. So why we can use that? Okay, just think of this way. So in the increasing queue, we're gonna save the pre-sum of the at so far at the current position. Let's say in the increasing queue, we have a pre-sum equals to 3, right? Sorry, not this one. Uh, let's say in this here we have a uh, 1, 4, 1, 4, 5. Okay. Let's say currently we have a this is a pre-sum, right? At each of the indexes. So we're gonna save the indexes here, but I'm just using this thing I'm using the value to better explain this how this increasing queue works. So let's say now we see a sum 2, right? Let's see we have a sum 2 here now. This is the new value here. So what is 2 is telling us, right? So basically, okay, now we have a smaller value, right? So whoever is greater than 2 will not will not be a valid candidates. Why, right? Because think about this. So the 2 has index uh, greater than this 4 and 5, right? But it also has a smaller sum, right? So remember, the way we're calculating we're calculating the range sum is by using the current sum, right? Sum right, right, minus sum left, right? And this sum left is the one we are storing in this increasing queue here. Basically, the smaller sum we have, the bigger result we'll eventually get, right? With this 2 here, when we use the sum right to minus to subtract this thing here, since this 2 is smaller than 4 and 5, so with 2 here, we'll definitely get a, a bigger sum. And the index, since the index is greater than 4 and 5, and when we in the end, and basically we'll definitely get like a shorter subarray while have the we'll also have a bigger a greater sum, right? So which means with this 2 here, it will basically certainly give us a better outcome than the 4 and 5, right? That's why we can simply remove the 4 and 5, because with 2 here, we know we can always use this 2 to give us a better result, right? That's why we can keep this like keep this array short so that it can help us eliminate some of the the invalid candidates, right? But when we see 1 here, then okay, we cannot remove 1 because 1 is smaller than 2, which means even though 1 is like will give us a longer subarray, but this one might give us a bigger k, right? We don't know if this one will we don't know if this thing is either a valid or not. That's why we'll keep this one in this increasing queue. And since it's increasing, which means even though there's another 2 here, right, we'll also remove this 2, because even though the result is the same, but with this one have a later index, it will also give us a better result than the 2, because that will give us a shorter subarray, right? So basically, every time when we reach the a new right here, we are maintaining this increasing queue, and also when we reach the new right index here, we can simply try to loop through from the increasing queue, because this increasing queue will be giving us all the candidates, right? So how we do the loop here, we basically loop from the start to end, right? We find, okay, so if with the current right sum, if it's the minus the subtract this sum, right? Can it give us at least k? If it can, we keep going, right? We keep going until the because this is like the increasing queue, right? So every time when we move forward, we'll definitely get a smaller k, a smaller sum, right? Smaller sum, and then in the end we stop until we reach the a place where the range sum is smaller than k. Then we cannot uh, keep going, because we know at this moment it's an invalid string. It's an invalid subarray. So that's when we need to increase this right pointer again to hopefully give us a better result. Mm, Uh, basically, we try the a new right pointer, right? And then we do this over and for the entire string. Uh, okay, so with those being said, let's try to write the code here. Uh, length, do a length n here. So, like I said, we need to do a pre-calculation on the pre-sums here, right? So pre-sums, the first one is is the first element itself. Okay, so actually the since we'll be doing the current one minus the uh, because for the first element, right? For the first element, and we will still try to calculate the pre-sum, right? And we'll try to use the pre-sum to calculate for the first element. That's why we'll have this like 0 as a base case to yeah, let's keep it at 0. Or let me think, can we, you know what, I'll just keep it 0 here. And then we'll do a for loop here in in range in range A, in range N here. So pre-sum pre-sums append, right? Append the current AI plus the pre-sums, right? That's always going to be the last element. All right. And then also increase Q here. Increase Q collections dot DQ. And then the answer, right? The answer, since we're getting the minimum, we initialize it to be the maximum, right? And then we do a right pointer, right? And the current as, we simply do enumerate the pre-sums. Okay. So we enumerate the pre-sums here. Basically, while, right? So like I said, we with the current sum, we'll try to calculate the answer here, right? Basically, if the increasing Q is not empty and as minus, right? Minus the pre-sums dot pre-sums Q, which is the minus one, right? Sorry, 0. It's at least K, right? And then we simply update the answer. So minimum is to right minus the increasing Q dot pop left. All right, so I will explain the pop left here about why we can remove it after we are processing it. So here basically we're trying to see, okay, with our current accumulated pre-sums, right? And then we're trying to check from this increasing Q, from this increasing Q here, if the smallest number for current increasing Q is the difference is greater than K, then we know, okay, this is a valid subarray, right? Then we'll update this answer with the current index, since we're storing the index in this increasing Q. That will give us the length of the subarray. And why we can remove it, right? And why we can remove this element after uh, after we have processed this thing as a valid a number, right? It's because and because because since we're popping from the left, right? We're popping from the left. The left side one It's always have the smallest index in this case, right? And for this while loop here, right? For this while loop here, and if we have this index, if we have the have process, we already find the this one to be the one of the valid subarray. Once after we processing it, we don't need it anymore because later on, if we find another valid subarray, it will definitely have a smaller length, right? Because we'll be finding another candidates on the right side, which will be having a bigger index, which will be in results give us like a smaller subarray. That's why we can remove this element once we know it's once we have processed it as a valid subarray, right? That's how we update our answer here, and then in the end we just need to maintain this increasing queue here, and s is smaller or equal than the pre since we're storing the indexes, right? That's why we'll need to use the index -1, right? That's the first element of this array here, of this increasing queue here. And we just do a pop, right? And then increasing queue dot append with this like the index, right? So in the end, we simply return the answer if the answer is smaller than the system max size, else -1. Okay, so let's run it. Yeah, so passed. Basically, the main idea here is that how we can efficiently, with each new right pointer, how can we efficiently search which arrays can give us at least k, uh, k sum, right? So two idea here, so two things here. First, we use the pre-sum to calculate the range sum, right? And then the second one is we use the increasing queue to keep the candidates because the increasing queue can can help us eliminates the worst candidates. And meanwhile, once we have processed the the element, it can also remove it because we don't need it anymore, right? Uh, okay, I think yeah, I've explained maybe too much about this thing. I don't know if I'm making sense to you guys, but anyway, I hope you guys can understand the idea behind this problem. And thank you so much for watching the videos. And I'll be seeing you guys soon. Bye bye.